Okay, so now let us look at some factors that they are going to affect the value of the equilibrium constant, either in terms of Kc or in terms of Kp. In the previous lecture, I said this. I say that Kc and Kp are temperature dependent constants, and the value of Kc and Kp will only change if and only if temperature changes. If you are going to add extra reactants, extra products, or you're going to increase the pressure, you're going to add a catalyst, all these, okay, all these are not going to affect the numerical values of Kc and Kp. The numerical values of Kc and Kp are going to be unaffected by changes in concentration and pressure or the adding of a catalyst. Now you might ask me, why is this so? Okay, now let us just continue first. Why is it that temperature has such an effect on the equilibrium constant? Now let us consider an endothermic reaction. So if we are going to increase the temperature of an endothermic reaction, an endothermic reversible reaction in dynamic equilibrium, this is going to increase the value of either the Kc, or if you write it in Kp, it is also going to increase. Let us consider this equilibrium, which we have gone through in the previous lectures. N2O4 being converted into NO2, a colorless gas being converted into a dark brown gas. We know that the enthalpy change of the reaction is more than zero. This means that it is positive, and the forward reaction is endothermic. Now, if you are going to raise the temperature by Le Chatelier's principle, the system is going to adjust itself by removing the excess heat. Okay, and you know that Le Chatelier's principle just means in general that it will remove whatever disturbance that is happening to the system. So the equilibrium shifts to the right. Okay, and the forward reaction, the endothermic reaction, is favored to reduce the temperature. And more NO2 is being produced. Now, the Kc expression for this reaction is the concentration of NO2 raised to the power of 2 and divided by the concentration of N2O4 raised to the power of 1. Now, what just happened is this. The numerator has just increased in value, okay, but the denominator has decreased in value. Okay, what happens is that now Kc becomes larger, okay, compared to when the temperature was slightly lower. Okay, and all this is because the forward reaction is endothermic. The temperature is raised and the Kc increases. See the relation now? Now remember this, temperature not only affects equilibrium, it also affects the rate of reaction. Remember this, when we dissolve coffee in a cup of ice cold water, it's not going to dissolve, it's going to take a very long time. But if we dissolve coffee in 100 degrees Celsius boiling water, the coffee is going to dissolve almost immediately. Okay, so temperature does have an effect on the rate of reaction. If you are going to increase the temperature, okay, this is going to increase the rate of the forward reaction, the rate of the backward reaction. Okay, but the increase is to different extents. Okay, if you compare this to the use of a catalyst, the use of a catalyst will actually increase the rate of the forward reaction and the rate of the backward reaction to the same extent. Now here it is. If you are going to increase the temperature of the reaction, now both the rate of the endo and exo reaction is going to increase, but the rate of increase of the endothermic reaction is going to increase more than the rate of the exothermic reaction. Now this means that the endothermic reaction is being favored when we increase the temperature. Now, conversely speaking, if we are going to decrease the temperature, the equilibrium constant of the exothermic reaction is going to increase. Now, this is purely by Le Chatelier's principle, because when we want to when we cool down the system will try to react in such a way to release extra heat so as to bring the temperature of the system up. In that way, more products will be formed. So if you remember, the product, the products of the product, okay, when you multiply them together, okay, the product is at the numerator, right? Is on top of the line in the division. Okay, so if this number is going to be bigger, this means that the equilibrium constant is going to increase. Now, some of you may be asking, how does Kc remain constant with changes in concentration? As usual, let us consider an equilibrium in action. An equilibrium is being set up over here. We have AB being converted into C and D. Now imagine we have a 1 liter reaction vessel, and we have X mole of A and X mole of B and Y mole of C and Y mole of D in that container. So at equilibrium, this is going to happen. A certain portion of A is going to react with a certain portion of B, and let us assume that that portion is known as Z number of moles, and that is going to give us Z number of moles of C on the right hand side and Z number of moles of D on the right hand side also. So for the Kc, okay, the concentration is the Kc expression is given by the concentration of C and D. You multiply them together and you divide it by the concentration of A and B multiplied together. So you can see that there is an increase of concentration of C and D compared to the original concentration, and also a decrease in the concentration of A and B compared to the original concentration. Now, what happens if we add P moles of A into the reaction vessel? This time, the concentration of A is higher than expected. Now, this time, the concentration of A is not expected to decrease. In fact, it increases. Now, what happens? Because everything is kept at a constant temperature, when A increases, Kc must remain constant. Okay, it must remain constant because it is the same temperature. We are not changing the temperature when we are increasing the concentration of A. So, how do we keep the Kc constant? Okay, Kc can be kept constant by us having an increase the concentration of C, and the concentration of D will also increase, and the decrease in the concentration of B. Okay, let me say that again. If we keep the temperature constant, Kc must remain a constant, but now we have a higher concentration of A. So how is it that the Kc can be kept constant by the system? This can happen if C and D increases. Okay, the concentration of C and D increases, and the concentration of B decreases. You must take note of this. The extent of increase in the concentration of A must be greater than that in the decrease on the concentration of B. Okay, this is because only then can Kc remain a constant by the system adjusting all these concentration changes.